Hello class. In this video we are going to discuss in detail the terms speed and velocity and talk about the similarities and differences between the two. Speed is a term that describes how fast an object is moving. Essentially, it just tells you how much distance the object is going to cover in each second. So if we look at this graphic down here, we can see that these objects are moving at two different speeds, and dots are being made at each second. So this blue dot is covering about 18 meters each second. That is its speed. Where the red dot is only covering about looks like 6 meters each second. That would be its speed. 6 meters per second versus 18 meters per second. You can tell that these are definitely two different speeds. The blue dot is moving a lot faster. The red dot is moving a lot slower. Speed is just a scalar quantity. It just tells you how much distance the object is covering each second. And remember, distance is also a scalar. So it does not at all indicate direction. Think about the speedometer on your car. All that information gives you is how fast you are moving. It does not tell you if you are moving north, south, east, or west. It only tells you your speed. There is no direction information given at all. So keep that in mind. Speed is a scalar quantity. And the SI unit for speed that we are going to be using is the meter per second. As we discussed in class, speed is a useful piece of information, but it doesn't give us the full picture. These two balls, which are bouncing back and forth, are pretty much moving the same speed the whole time. But if you notice, they are constantly changing direction. Sometimes they are moving to the left, and sometimes they are moving to the right. So speed doesn't differentiate when these balls are moving in one direction versus the other. So we need another descriptor, and that is where velocity comes in. Velocity is essentially the vector version of speed. It is speed combined with a direction. So it describes how fast the object is moving, that's speed, and also in what direction it is moving. So if we look at this ball bouncing back and forth, this arrow here is the velocity vector. It is showing the direction that this ball is moving in at all times. And this information is a little bit more powerful. It allows us to truly know not only how fast the object is moving, but also where it is moving, in what direction is it traveling. The symbol for velocity that we are going to be using is a lowercase v with an arrow on top. This arrow on top reminds you that velocity is, in fact, a vector. And the SI unit for velocity is also going to be the meter per second. Now, as a reminder, I've probably said this 5 times so far, velocity is a vector. So if we are describing the velocity of an object, we need the two things that a vector needs, both magnitude and direction. So if I were to describe the velocity of, say, a moving car, the car might be moving at 2.3 meters per second to the east. The 2.3 meters per second, that is the magnitude, and the east describes the direction. Now using a vector arrow, if we wanted to show this in a diagram, the magnitude would be 2.3 meters per second written below the arrow. Then you just point the arrow in the direction that you want. Now, this whole thing, magnitude and direction, is velocity, but as we said, speed is also included in this information. The magnitude of the velocity vector is automatically going to be the object's speed. So if the total velocity is 2.3 meters per second to the east, then the object is moving at a speed of simply 2.3 meters per second. So velocity clearly seems like a really important concept in physics, and it is. So wouldn't it be great if we had an equation that we could use to quickly calculate velocity? Well, turns out there is, and we already did this in class. As a reminder, we determined that the slope of this linear position versus time graph is going to represent the velocity of the object. So we can use that information to actually calculate what the velocity of this object is going to be. So we know slope is equal to rise over run, or change in y over change in x. We already determined that the slope is equal to the velocity. So all we need to really determine is what truly is the change in y and what is the change in x. So the change in y is going to be the change in the object's position from this location to this location. It starts here and it ends here. So this delta y, this change in y, is going to be the object's change in position, or its displacement. So really, in the top of this fraction, rise over run, we are doing displacement, change in position, in the numerator. In the denominator, we have this interval of time, the time interval lasting from here to here. We have time interval delta t. So we can plug both of these into the equation, and we realize that the velocity of the object is just going to simply be the displacement of the object divided by the time interval it takes the object to travel this specific displacement. And this might look a little bit familiar if you're familiar with the equation for the speed of an object, which is simply distance over time. Well, velocity is just the vector version of that. Instead of distance, we are going to be using displacement, but the time interval stays the same. Now, one thing I want to warn you of, because we developed this from our constant velocity model, this linear position time graph means that this is a constant velocity situation. This equation can only be used when the object is moving at that constant velocity. Once we get to more tricky situations where the object is not moving at a constant velocity, this equation cannot be used. So always keep in mind where these equations are coming from. They do not apply to every situation. This one only applies to constant velocity. So, in summary, two really important terms that are going to get us started with this unit of kinematics. Speed, which describes how fast an object is moving, and velocity, which is this vector quantity that describes both speed and direction together.